Hello, hi, I'm Eric Brynjolfsson. This is the Digital Economy Lunch Lab Seminar. And today's seminar speaker is going to be Neil Thompson. I'm going to give people just 60 seconds to file in here and online, and then I'll introduce Neil and we'll start the seminar.
Good to see you. I knew you were going to go.
Welcome to the Digital Economy Lab Lunch Seminar. Today's seminar speaker is Neil Thompson. Neil is the director of the Future Tech Research Project over at MIT, where his group studies the economic and technical foundations of progress in computing. He's also cross-appointed in MIT's Computer Science and AI Lab and MIT's Initiative on the Digital Economy. Neil was a colleague of mine back at the MIT Sloan School, where he directed the Experimental Innovation Lab, and a visiting professor at the Lab for Innovation Science at Harvard. He's advised businesses and government on the future of Moore's Law and has been on National Academy's panels for transformational technologies and scientific reliability. He's part of the Council of Competitiveness's National Commission on Innovation and Competitiveness Frontiers. His PhD is from Berkeley in Business and Public Policy, where he also has master's degrees in computer science and statistics and a master's in economics from the Lund School of Economics. He's worked at organizations like the Lawrence Livermore Lab, Bain & Company, United Nations, the World Bank, and the Canadian Parliament. We welcome and encourage questions during the seminar. If you're in the Zoom audience, please submit your questions using the Q&A function on Zoom. For those of you here at Stanford, just raise your hand and we'll call on you to ask a question. I might repeat, or one of us may repeat the question for the people on Zoom. And Neil, so how do you feel about questions? You want to sort of save some time at the end for a broader discussion and take clarifying questions during it, or?
Sure. I mean, if someone has a very long question, we can save it to the end. If it's quick stuff, I'm happy to just take as we go.
That's a good format. All right, so welcome to Stanford, and please tell us a little bit about which costs are cost-effective to automate with computer vision. Thank you, Neil.
All right, thank you very much. And can the folks online still see me if I'm over here? Okay, excellent. Great. So thank you so much for having me. So this is a project that I'm quite excited about. It has been amazing. I think it's been 3 or 4 years we've been working on it. You will see why as we get into it. But this work is going to try and build on some of the work that people like Eric have done in terms of thinking about actually where we might see AI automation. And in particular, a really central thing we're going to come to as we think about this is jobs. Okay? It's, all over the news about this question of, well, what jobs are going to get replaced, how many, and particularly some of the early work in this area was very shocking in terms of the numbers. So PricewaterhouseCoopers said that by 2030, 50 million jobs in the US economy would be automated by AI. Bank of England did analysis by 2035, 80 million jobs. So to put that in perspective, right, the US labor force is like 160 million. Right, so this is saying like half of all jobs gone. That would be really big number. Okay, so the question is, like, is that going to happen? And also, more broadly, how should we think of the job replacement that we're going to get from AI? And the reason I say it that way is because I think we have these competing analogies for what AI job replacement is going to look like, and they have vastly different implications in terms of public policy. So what do I mean by that? Well, there's a version of this which says automation is going to look like what we've seen in automation before, right? We had a huge percentage of the labor force working in agriculture. We figured out how to automate a huge portion of that work. Now, very few people work in agriculture. And there were some transition costs, but ultimately, people sort of reallocated, and it was all right as a society. The other option is mass unemployment, right? The automation just happens too fast, right? You can imagine a world where even sort of humans who lose their job start retraining for another job. Before they can finish that retraining, the AI is better at that task too, right? And you end up in a world where you get systematic and wide-scale unemployment. Okay, so this question matters a lot, and we are, as I say, we're specifically going to be thinking about this job replacement question. Now, like others, when we think about this research question, we're going to ask this question in the context of particular tasks. So we're going to say, what share of tasks is it economically attractive? I'm going to come back to that in a second, to replace human workers with computer vision AI. And then how is this going to change over time? Okay, so the tasks part of this is just because as some of the work by David Otter and others have really made clear, as compared to some of the very early work in AI, where people were thinking about sort of, well, if you have some exposure on your job, then your job is really very much at risk. And it's like, well, wait a minute, maybe only a little part of your job is at risk, right? We shouldn't overgeneralize to what's going on here. So we're also going to look at this at the task level, but then we're going to sort of add up all the little pieces of tasks and ask across the economy, how big does this affect? Okay, and then we're going to ask how this will change over time. Sure. So computer vision here meaning like one of the sort of central early things that deep learning was able to do very well, which is to take images of things and recognize what's in them, demarcate where things are, those kind of things. Those are the systems we're going to focus on directly. Now, I think perhaps getting at your question, as I suspected in the back, is there's also a question of what can computer vision teach us about AI automation more generally? And in fact, we will go to there right at the end of the talk. Okay. So what we're going to model and what we aren't going to model, okay? So what we are going to model is substitution. This idea that there's a human doing a particular task, and we say, okay, could we build an AI system to do that task as well as the human does, right? And we're going to say, if you can do it as well as the human does, that's the mark where you'd say, we're probably going to lose that person if we choose to automate it, right? So it has to be economically attractive. But if we choose, that's the point where you would want to do it. So Eric has called this Turing trap automation, right? And this is, I think, a really useful term in this context because it's not at all obvious that this is sort of a great thing for society, right? Because if the system is just doing what the human did, right, we haven't gotten a bunch of extra productivity, we haven't gotten a bunch of extra capabilities or so on. We've just taken the human out and replaced it with a machine. We've reallocated those wages, but like we shouldn't expect a ton of economic growth coming out of that. And so this sort of, if the pie isn't getting bigger as we do that, we should worry about that. Okay, what we are going to try and model here, and not because we wouldn't love to, but because it would be incredibly hard to do, is the sort of, well, if all of this comes in, right, people are then going to start to say, well, I'm going to totally redesign my business processes, right? Now I have this tool that can do this cool thing. I'm going to have a different business model. I'm going to have a different flow and stuff like that. And of course, asking that question of what are the hypothetical organizations that might exist and the hypothetical products that might exist is going to be well beyond what we're able to tackle here. Okay. All right. So that's where we're going. So the agenda here is then going to be to start by laying out this framework for what AI cost effectiveness. So how can we even think about this question? Then we're going to estimate the share of task replacement that is economically attractive to actually do. Then we're going to simulate how AI could actually spread. So we're going to have a momentary thing that says, today, what does it look like? And then we're going to say, well, what if we had more deployment of AI platforms or lower cost, right? What would that do to the spread of these AI systems that we're going to have? And lastly, we'll discuss how this fits into the larger framework of what AI can do, not just in computer vision, but more broadly with language models. Okay. So if we think about sort of the broad way that a lot of this analysis has done before, it's been saying this very useful, but I would say just first step in the process, which is, could an AI system do a particular task, right? So call this AI exposure. And so you can think of this in the following way. So we, like many people in this area, are going to use the ONET database from the Bureau of Labor Statistics. And if you look inside there, you're going to get these job descriptions. That's going to say, oh, okay, if you're a baker, you have a series of tasks that you do. You check products for quality and identify damaged or expired goods. You make dough according to recipe, etc. There are a whole bunch of things. And then you would say, well, okay, we have a particular capability here, which is computer vision. And we're going to ask, could computer vision do those things? And if you look at that list, you'd say, well, that first one, probably, at least in theory. You could imagine putting the camera on top of it, and as like ingredients come out of the fridge or something like that, you're like, oh, this looks like it's gone bad, throw these apples out, whatever. Okay, all right, so you can imagine doing that. Computer vision, not gonna be able to mix dough according to a recipe, right? Okay, so you'd say, all right, so there's some risk of AI exposure for this task, not for this task. Okay, of course, the problem with this, and where is gonna be the sort of heart of this paper, is the economics of this question. So let's imagine that we're doing this baker, and you actually look, about 6% of a baker's job is to check these products for quality. Okay, great. Cost to a baker, to their employer, $48,000 a year on average, according to the census. Okay. You have a small bakery with 5 bakers, 48,000 times that 6% times 5 bakers, $14,000 a year. That is way less than it would cost to build a system to automate this for you. So yeah, it could be, but you wouldn't want to, right? So this job is maybe not as at risk, particularly in a small bakery, as it would be elsewhere. Now, of course, you might immediately jump to, well, what if it's a very large bakery? Then you might have it. And that's going to be one of the key insights of this model, is that you're going to get this differential where a bunch of tasks, it's not that the task as a whole gets automated, it's that it gets automated in some places and not other places. And then you have the slow diffusion as people start to build AI platforms to be able to make it spread through the rest of the economy.
Could you say a little bit more about the cost side? Like, I guess my iPhone has some pretty good cameras in it. And I haven't ever tried to build a vision system, but would this hardware connected with some other software be able to do some percentage of that task?
So certainly could, right? So in many of these cases, you can imagine just sort of like a webcam and an engineer's time for a little bit to set stuff up and set it. Now, that's sort of the very low end, right? If you didn't have to have a particularly high level of accuracy. If you needed a very high level of accuracy, right, you probably are going to have to gather your own data, do your own training. That's going to make it much more expensive to do all those pieces. Yeah. And so we should think of there being sort of some deployment cost, which we'll actually sort of test as we get later here about. And so we did a whole bunch of case studies for this, and we saw that it's often like when people are using vision systems, it's often hundreds of thousands or millions of dollars they're spending right now. Now we assume that will go down over time, but actually doing these things and building it in could be very expensive. Right. Okay. So if we then think about the work that has come before and what we're going to do with it, you can think of the list of tasks done by workers in the economy. That's that ONET data. And as I said, the AI exposure, the previous style of doing this, is to classify tasks by similarity to AI capabilities. And so this can be measured by machine learning experts. People may be familiar with the GPTs or GPTs paper. So that was one where they asked computer science experts and said, hey, do you think that this system could do what the baker's doing, right? You can ask patent language. You can use patent language and say, oh, people are discovering ways to do these things. That indicates that the system has some of those capabilities. That similarity might be an indicator. So these are the kind of things people have done before. What we're going to do is we're going to start by actually surveying task experts, not machine learning experts. We're then going to take their answers about the performance that's required for something, and we're going to say, well, how much would it cost to build a system that has that level of capabilities? And then lastly, we're going to say, okay, at the level where this is going to be adopted, does that mean the economics are attractive or unattractive for actually adopting? Okay. So in our view, there are sort of contributions to all three of these. So the first one, I think a really important thing here is just that, of course, if you need to get information on both, like what the task is doing and what machine learning can do, it's pretty hard, right? You don't have a lot of bakers who are also machine learning experts and they're part-time, right? And so you often have to sort of like make a choice between these. And I think the GPT paper, for example, has done a good job. I would have chosen, if I only had to pick one, I would choose machine learning experts as well. But I think what we're going to be able to do here is we're going to be able to say, well, if we can build in the second part, that cost model, that means in the first part, we can actually ask the people who are right on the ground. And they can tell us, oh, this system, you might not realize it, this system has to be incredibly good because there's something else later in the process that depends on it. And if you are less than, make more than 3% errors, actually that's going to ruin something later Okay, so that's the benefit of the survey. The real heart of the paper is going to be saying, well, how do we even build a cost model? How could, like, that second piece seems like it might be incredibly hard, and that's in fact what took so long, which is why I said it's 3 or 4 years. And then of course that last piece is just going to be then taking that cost model and applying it. That's the part
Oh. Feel free to defer the question if you're going to cover this later, but it seemed to me very challenging to build the cost model because, you know, as we're moving down the learning curve, those costs are probably rapidly declining, you know, along the lines of Eric's comment about, you know, we could use existing off-the-shelf hardware. These things are changing very rapidly, right?
Absolutely. Okay, so I will address part of that over the next about 5 slides, and then I will come back to a little bit more later in the presentation as well. All right, so let's start at the theoretical level. Why should we hope that we have any chance of doing this cost estimation at all? And the answer is AI scaling laws. So for those who haven't seen it, this is a very complicated figure, but it's I would say one of the most important figures in AI that has come out. So this is from a paper by Hennigan et al. Back in 2020, and it's talking about scaling laws in AI. So let me talk you through it because there's a lot going on here. Okay, so let's start with images. So this is, we're having a system and we wanted to recognize what's in the images. Okay, and on the x-axis here, we have the amount of compute. And notice this is a logarithmic scale. So that's a 100-fold increase in compute, another 100-fold increase in compute, and so on. And on the y-axis, we have the errors that the system is making. Okay, so we can sort of test it in much ways, and you can see that here we have, again, a logarithmic scale. So these are log, so these are polynomials that we're measuring here. And each of these lines that you're looking at is a trace of a particular training run. So for example, if you took a system that had 1 million parameters, which is what the colors are representing, 1 million parameters, and you take it down, you see that initially it doesn't do very well, and it improves quite rapidly, and then it hits that dotted line along the diagonal, and then it comes across. Okay? So that's telling you that that's where that system is. Now, if I increase the number of parameters in the system, now I'm at one of these lighter color lines, and I come down much further, but then again, at some point I cut off. Okay, so what that's telling you, right, is that these different lines trace out this diagonal line. That diagonal line is then telling you, if you tell me the amount of error you want for your system, I can tell you the amount of compute that will be required and the size of the model that is optimal to choose, and therefore the amount of data that you would need to do, right? So you can back out, this is a recipe for saying, what's the system you actually have to build to actually get the amount of error that you want to have? Okay, so now all of a sudden, right, if we say, well, if we ask the experts using our survey, if we ask them and they said, your system needs to be 95% accurate, we can work back and say, okay, for a system to be 95% accurate, here's what you would actually need. And we can think about actually building such a system, right? We can ask them how much it would cost to gather data in their particular area, right? We can look at Amazon and places like that for how much it would cost to buy the compute. We can start to build this picture of the cost that would be involved in actually doing that. Okay, Eric.
I mean, these are amazing charts, and everyone should be familiar with them. There are 2 other things that are in the background. One is data, and we were talking about these charts in the office, but you also have to scale up the amount of data with the compute. But so assuming that's available, right? And also, this is with essentially the same algorithm. Like maybe people are inventing better algorithms, but are all these? Is that a correct interpretation?
So in terms of the algorithm question, I will come back to that a little bit later. I would say my lab was one of the people we studied scaling laws also back in this time frame. We were one of the first people to look at it across different models. And so even when you take into account all the improvement people are making, you still see these scaling laws. So you do see improvement, but it's just sort of like a translation of these scaling laws is the right way to think about it.
Right. That makes sense. But like, I take the blue line, the yellow line, or whatever. Does that reflect changes in the number of parameters, or does it also is there simultaneously changes in the way that they're run that's reflected in this? Well, I guess maybe I'm implicitly assuming that if you come up with a better model, it would be a steeper scaling law than if you didn't have a better model. And which one of those is shown on this chart?
So, okay, so this question about like what the new algorithms are doing is a very ongoing question. We're actually going to have a paper out in probably the next month that will talk about this. But what you can see is that there's been very rapid improvement, but it's mostly in how efficiently you can use data. And so what that means implicitly then is that you wouldn't expect the model size to change. You'd still expect to be on this, but you would expect that you have to use less compute to get that, for that same thing, because you're able to leverage it more efficiently. Yeah. So, okay, and then in terms of your other question, in terms of the actual amount of data, in all of these, almost all of these cases, we would expect there to be enough data for the kind of things that we're talking about here, right? That where we're really running out of data is on these like very large language models that are like very foundational. For the stuff where we're talking about, like for the bakery, right? It would be pretty easy for them to take pictures of the food, label it as not bad and not bad, and you could, it might cost you some money, but you could definitely gather quite a bit of data that way if you wanted. Okay. So I just want to before I move off this, because I sort of told you the part where how we're going to use it, but as I say, I think this is probably like one of the most important charts in all of AI, and it's because this also gives you a recipe for understanding how AI is developing. And so in particular, if you think about, I want to have the amount of loss that one of these systems are making. So if I have an image recognition system and I want to have the amount of loss, right? I use this line. If I want to have the amount of error for a system that goes from text to images, like generative, I can use this one, right? There's all of these things, and you always see this nice scaling law. And so what that's telling you is also how the compute is going to escalate. And so, we had those equations. I'm going to turn that into a little bit more easy version to think about. So if you wanted to have the loss for images, okay, well, for these very small images, 8 by 8, you need to increase the amount of compute by 40x. It's not too bad. Right, now, if you wanted to increase it and have it again, be another 40x, right? Because it's the power law. For text images, 100x, video 140x, math 140x, image to text 75. Language models, 1.9 million. Okay, so when we think about OpenAI, as we will a little bit later in the talk, right? And you think about these GPT models, right? What this is telling you is that continuing to improve those systems is going to get dramatically more expensive, right? And Eric, just before the talk, was showing me how Sam Altman is apparently asking for $7 trillion for the next stage of what he wants to do. So you can see why these things are going to escalate so quickly because of these language skills. Okay, all right. So even if you have this recipe, though, we're not quite done in terms of thinking about the cost that we're going to need for model we're going to do. And that's because you often require fine-tuning. And so what do I mean by that? Well, typically, these large foundation models that people have are trained on pretty broad data sets, right? From right here, right? The ImageNet data set. But if you actually look at it, and as I say, we did a whole bunch of case studies for this work, you end up with situations like this. So one of the case studies we looked at was somebody who makes parts for oil drilling rigs. Okay, great. And so what actually happens? Well, some person calls them and says, hey, I just sent you an email, look at it and send me the part. So person opens up the email and someone sends them, some mud-covered piece of this. And you're like, okay, I guess I'll just figure it out, right? And so you end up with this actually quite highly trained customer service person who looks at it and says, oh, that's part R23, and sends them part R23 in the mail. And this company said, okay, well, what we're going to do is we're going to automate the system so that when it comes in, it's going to say, oh, we think it's probably R23 or maybe R24, right? You pick which one to send. Okay. Problem is R23 and R24 are not in the data set that was trained here, right? If you use this system off the shelf, it's going to tell you cat, right? That's not very helpful. So you have to do this because the correct labels don't exist before you do the fine tune. Right? And so you're often going to have at least some retraining that you have to do. If for nothing else, then you just are using it for a company-specific reason. And those company-specific things usually don't exist in the overall data set. Okay. All right, so if we think of then the costs that firms have to get to actually build these systems, so there are a bunch of fixed costs, right? There are engineering costs. You have to have a team that actually puts it in place. You have to have some ongoing team that's going to be maintaining the system, right? These systems often will have drift or other problems. People may be trying to game them, right? So you're going to have some ongoing team looking at it. You have performance-dependent costs. So if I have a 95% accurate system versus a 90% accurate system, it's going to mean different amounts of training costs, different amounts of retraining costs, both in terms of compute data. And then you actually have your scale-dependent costs. Like you actually just have to run the system, and you might have to do that more under circumstances. Okay, so that's a big cost tree. As I said, we did a lot of different things to try and get hold of this. So we did 35 different case studies. We wrote a teaching note. If anyone is interested in teaching an economics of AI class, we have a case to show you. We did analysis of the AI literature. And unfortunately, even for part of this, we actually realized there was a hole that we needed filled. And so we wrote a computer science paper so that we could have the piece that we needed to do this. So when I tell you it took 4 years, there was like a little hiatus in the middle where we were figuring out the computer science of this one thing so we could keep going. Okay, so all of that then leads you to a model that looks like this. So you say, we have some original domain like ImageNet, where we have a pre-trained model that has some level of performance. Say, great, now we're going to take it to our new domain, right? Now we're looking at those R23 parts, right, for the drilling rig. And typically you're going to lose a lot of performance. Okay? How much you actually lose turns out to matter a lot about entropy. For those who don't work with entropy, this is just sort of a complicated way of saying it's actually sort of how many categories you have in the problem, right? So as an example, Boston Scientific does a whole bunch of work with stents, right? They use vision systems to help evaluate those. That's a pretty easy task in terms of it's good or it's not good, right? So the quality control part of it. So that means it's a relatively easier task than ImageNet, which has 1,000 classes in it, right? But you can also have the situation where it's a much more complicated problem, and that makes it even harder to. All right, so we move over to this new domain. You have some level of performance. You say that's not good enough. So then you say, well, here's the accuracy I need. And we have to do this fine tuning. And again, it turns out there are these scaling laws also exist for fine tuning. And so we can infer how much data you're going to need and how much compute. Okay, let me pause for a second because I've thrown just a bunch of computer science at you. If you like, the only crucial thing you need to know is there's the recipe that's going to take us from the amount of performance you need to actually like the elements of the cost. But I'm happy to answer questions that people have.
So I have one just in your very last comment. So there's scaling laws for the basic model, the foundation model, and then there's other scaling laws for fine tuning. So if you trained it on ImageNet, and now you want to add another 50 oil rig parts to it, what kind of order of magnitude of additional cost would that be? Or say 500 oil rig parts, but it's like way less than the original millions of ImageNet images.
Yeah.
So is that a material part of the training cost, or is it like a different order of magnitude?
Oh, a very different order of magnitude. These the transfer learning costs, unless you want a system that is incredibly good, are typically much lower, right? So you should be thinking of for the initial training, right? I mean, GPT-4 cost 100 million to train, right? These systems might be in the many of them would just be in the millions or hundreds of thousands, right? Yeah. Now, of course, if you still wanted, you set out, well, I want a system that's 99.9% accurate. That would cost a fortune, right? Because even the base models are not accurate. Okay. All right. Okay, so that's the framework we're going to use. Now we're going to estimate the task replacement that is actually economically attractive. Okay, so a crucial thing here is just going to be sort of economics 101, which says, well, if I have to build this big AI system, that's a big fixed cost, right? That means my average cost curve for the computer vision system is going to look like this, right? The more I can deploy it, the lower the average cost. And then I'm going to have some human, right? And here I've drawn the human as flat. You might have some training costs here as well, but I mean, for the sake of it, it's certainly relatively flatter. And so you say, okay, that's what that looks like. And there's going to be this minimum viable scale point where you'd say below that, you don't want to use an AI system for it, and above it, you do. Okay. That, though, is going to turn out to matter a ton. Okay, and let me give you the intuition, and then I'll show you the real numbers. So one of the tasks that retail workers do, that is a vision task, according to the ONET database, is to look at the shelves and to say, does the price that you have line up with the thing that's shown there? Right? You can imagine you don't want to label things wrong. Your customers get upset. Okay? If you're Walmart, you absolutely could imagine automating such a system. Right? You put a bunch of cameras in the store, they're looking at the labels, they're looking at the actual bottles, and they're saying, yeah, that lines up, that seems right, good. Oh, flag a problem over here. You're a little corner store, forget it. You would never do that, right? And so we're gonna have that divide where the really big folks are gonna wanna do it, and the little folks are not. Okay, so how big a difference does this make quantitatively? Well, across the US economy, about a third of jobs have at least some computer vision exposure, meaning the job has at least one task that could be applied by vision. If you ask the share that are economically feasible or economically attractive, now it's actually like 8 or 9%. Okay, about a quarter the other number. You can also look at this in terms of the total wages that we're paying those workers, and you get almost an identical view. Okay. So this is really telling you that there are just a whole bunch of small applications throughout the economy where if it cost you even a marginal amount, you'd say, actually, I'm not that interested in automating that with AI because the human is more cost effective to actually do. Okay. Now, I told you about this whole cost model. We're sort of estimating the value of replacing these by the humans, the wages that we're replacing. Let's actually get at a little bit of robustness check to know that this is not sort of like a crazy answer. So we can say, and I realize this slide doesn't have all the actual numbers on here, but you can change cloud pricing. This is like more than a 2x change in cloud pricing. It makes basically no difference at all, right? The high case and the low case. You can change the amount of entropy, which is like that task difficulty. Makes a little bit of difference, but not much. I mean, you see it's like 2%. You can change how long the systems can last, right? How long between you need to retrain them, get very little difference. How often you have to how accurate they are. But accuracy matters a ton, right? In particular, if this case is, if the tasks are harder than we're assuming they are, right? You need a higher level of accuracy, then the amount of automation you want to do falls way, way down because of these scaling laws, right? The cost escalates so fast because of these scaling laws that you don't want to do it if you need a higher level of accuracy. You can look at data costs, you can look at engineering costs, and you see almost all cases we're in this range of like 20 to 30 something low percent. So it's a pretty narrow range that we can have a fair bit of comfort that even if some of our assumptions are a little bit off, actually it's not going to really change the qualitative answer very much. Eric.
Can you say a little more about the firm-specific costs versus the, so like, I don't know, if Walmart, I don't know if they make their own shopping carts, but probably there's a company out there that makes shopping carts for lots of different retailers, small ones, medium ones, and maybe they have to customize and put their logo on it. So there's sort of, you can imagine that there's part of the application that's made that cuts across lots of retailers and parts of it that has to be customized or fine-tuned for retailers or for a particular firm. Can you say a little bit more about how to think about that and how that affects, like, it seems like the business model of how it's produced and how much can be generic makes a big difference about the fixed costs being spread.
Absolutely. So right now, we're taking the lens of the firm, right? For this. Now, in about 3 slides, I will actually show you how that changes if you say, well, could we build an AI platform that is going to do it in the kind of ways you're talking about? But I think your intuition is exactly right. The question is sort of like, how generic is this, right? If I train it at Walmart, does that carry over to, the H Mart that's down the street from me? And like, well, maybe in part, maybe not, right? And so you'd have to think about it. So yes. So this is why we choose to do it at the firm level, because it's, we actually say that's the unit that the decision making is happening, and you hope that it's pretty uniform across that. But indeed, we should expect platforms to start emerging, and that's one of the main mechanisms we expect to have an increase over time as people start building these platforms. And Walmart says, well, why don't you use our system? And you can use it, strap your iPhone to the roof and, of your store, and we'll use it for you as well.
It's totally a minor point. Thinking about it. Sorry. Yeah, it's a minor point, but I keep thinking about this way in which you're comparing smaller firms with larger firms. And I don't know why that is important. In the end, if this works, you'll have a robot show up at your place at 9 o'clock at night. It will let itself in. It will go up and down the aisles. Doesn't matter what size you are. It will determine whether the prices are lined up with the things, and it will leave. And if you're small, you have a managed service provider that provides that thing that visits you and does that in an hour's worth of work. And if you're a large person, you own it. So I guess I'm trying to understand why make the distinction between the cost cutoff of a size of firm. And as I said, it's sort of minor, but I keep hearing it, and I'm not sure why it's important.
Yeah, so I think the answer is just how fast you should expect AI to be through the economy. So if you say, hey, 40 years from now, like it should make no difference what the business model is. Like if the system can do it, and ultimately there's enough spread that you say, like, we want to build a system that does this, then I agree with you. You would expect like lots of people to build AI as a platform systems, and they would sell it to you, and they'd say, hey, come and do this, and our robot will come into your store and do it for you as well. Absolutely. But in the interim, you still have this question of saying, well, like Walmart builds this first, right? Or Google or somebody builds this first. Then they have to say, well, on what training set? For what client? And presumably they're going to do it for the headline clients first, right? They're going to say, oh, we're going to build the first system for Walmart, right? And then we're going to try and think about how to broaden this out in a way. And the problem is that broadening that out is going to require fine-tuning it, getting more data for it. Like there's going to be lots of things that you have to do, and that's going to slow the pace of the automation in a way that's going to change it from being like it all happens right away to it takes a little bit of a while. And in fact, what I will show you in a little bit is some curves where you can start to think about, well, how fast do these things have to change the answer that you get here?
And let me just get a question from online here. Zubin Wadia asks that right now, cost to consumer are often being subsidized by the sheer scale of capital and GPU credits being deployed. Does this distort the attractiveness curve, making more use cases economically viable than they would be under your analysis? So I think the idea is that some of these costs are being subsidized by...
Yeah, exactly. So in general, yes, subsidization will make this more attractive. Unless you're doing a really cutting edge system, the compute costs are not dominant enough to make a big difference. So the compute credits themselves are not going to push this around very much.
So I have a question. Help me if I understood this well. There's an assumption that the cost is allocated to the same entity. So the training cost is allocated to the same entity as the fine-tuning cost. But what actually we see in deployment is that the training cost is usually shouldered by the company, the developer, and the fine-tuning cost is typically shouldered further down the pipeline within the firms. So how does that play out? Is that a concept?
Yeah, so that's a great question, and thank you for clarifying, because I realize this is just a sort of confusion in the way that we've done the labeling here. So when we say training labeling on this, we mean just the fine-tuning training, not the underlying model, because exactly as you said, typically you would not expect those original costs to be carried over. Now, of course, the fact that they aren't carried over, you should worry about that a little bit if you're the firm building the foundation model in the first place. But yes, but from here, we're only talking about the costs that are site-specific for your firm or your platform. Yeah. Okay, so now I want to go back to this idea of the value that's being created here. So in all of these calculations we've done, what we've said is, well, take that baker example, right? We had those 5 bakers, 6% of their time, and we said, okay, here's the sort of wages that you could save if you didn't have that, right? And we think that's the right comparison because remember, we designed these systems to be exactly equivalent to what the human was doing, right? So we're saying, okay, you get that cost savings that comes out of it. But you can say, well, now AI systems have a lot of other things going on, right? Like maybe if I create this AI system, I can run a third shift in my factory, right? And I don't have to pay any extra for that. That might be really nice for me. So you can modify it and say, well, what if instead of the value being created as being 1x the human, right? What if it was 2x or 4x or 8x, right? Or maybe you think it's the other way. Maybe you think these systems are brittle and hard to, hard to manage and stuff like that, and you think there's less stuff. Okay, so here you can see, indeed, it does make a difference. But what I want you to notice is these are logarithmic, or let me say exponential differences, right, in the amount of value being created. And we're only getting a linear change in the amount of ones that are attractive to do. Okay, so this is going to be really important when we get to the cost stuff that's going to come later. But this is just reflecting the fact that there is this very long tail of tasks, and sort of moving out of that tail, you've got to get a lot cheaper or a lot more value in order for it to be worth doing. Okay. All right. I also want to show you that this actually is nice and is usefully predictive. So this is some work that Frank et al. Did, saying, okay, well, there are a whole bunch of different measures that people have put together for automation that's going on, right? And they said, okay, well, how well can that predict unemployment risk by occupation, month, and state? So what they're doing is they're aggregating up unemployment risk that has happened at the state level. Now it's at a pretty aggregated level. It's at the 2-digit SOC level. So this is like pretty high level, right? But what you can see is that our measures here, even though we're only predicting computer vision, explains more of the variance in this than do these other. Okay, now let me pause for a second here, because you might be saying, whoa, it's really 10% of all unemployment, like explained by computer vision over the 2010 to 2020 period. And I think no, right? Our measure, just like the other measures, is going to be correlated with a whole bunch of other stuff that makes other things attractive as well, right? And so we have to sort of be careful about this. This is just sort of supportive evidence. We shouldn't think of it as being causal, that is the share. But it is telling you that our measure is doing quite a good job of explaining what is attractive and where it is attractive to do that operation. Okay. All right, so now let's, a bunch of you are sort of pushing me in this direction of, let's think about these platforms and let's actually do that. And you will see that, boy, it changes a lot, because that value, right? We're always comparing the cost and the benefit. And what we're going to see is when you increase to the size of the whole sector, for example, you get a lot more value. So that's going to be the first thing. Then I'll also look at sustained reduction in development costs, which was also brought up, to see how much that changes things as well. Okay. So the question here is going to be, how broadly can you actually deploy it, right? So in ImageNet, in ONet, you have these descriptions of tasks, and sometimes you see it not just in a particular area, but more broadly. And so we might have it at the level of a firm, but then you might say, okay, well, maybe you could take your system that is being used to recognize food quality, and maybe that would apply to your whole industry group, right? So these are going to be related to, but your industry group has like bakeries and tortilla manufacturing, maybe that could apply. Now you might think maybe not, right? Maybe like, at the level of my bakery, I was looking at apple pies and I was recognizing apples. Maybe that doesn't tell me a lot about tortillas, right? And so we should worry as we move this way that you're assuming the system is a lot more general, and it usually a much more general system is much more expensive. But as we go, we can say, well, what about the whole subsector? Maybe we can detect all bad food in the food manufacturing area, or all the way to the full economy. Okay, so that's what we're going to mean when we say AI is a platform. We get to spread out these costs and deploy them over all of this area. What a difference it makes. Okay, so at the level of individual businesses, we get what we saw before, which is that 23% of all of the ones where vision could be used, it actually would be economically attractive to. You get to the level of the industry group, now more than 80%. Right? So I think this is what you're talking about. Over decades, you should absolutely expect that these systems would keep going, right? As long as you're able to leverage the Walmart system for all the small ones, right? As soon as you get to a point where you have to design a special system for the small ones, then you probably don't want to do that, right? Okay, so this is telling us three big things, right? So most firms lack the scale to automate tasks. Platform systems deployed across industries do have that scale. And even at the level of the whole economy, some systems are too expensive and you still don't want to deploy them, right? So this is, sort of encouraging from the point of view of like, labor may still have some things to do, because there are just cases where like the level of proficiency that's needed would just be too expensive. You don't want to build that using the system technologies that we have right now. Eric.
Does this curve correspond to the logarithmic effect you showed earlier, that as you got bigger and bigger, there's this, I guess I call it long tail or whatever, these tasks that are getting very idiosyncratic, very expensive. And even if you get to the whole US economy, some of them are still just too expensive too.
Exactly, right? What's happening is you go to the right, you're getting more scale, and that helps, right? But there's some tasks that are just rare even in the whole economy. So you don't want to do those. And there are other tasks where the accuracy you need is just so high that you just don't want to build the system.
So most of the difference in scale is between small businesses and the industry. The difference between industry and economy is not that big.
And you can imagine why that's true, right? Because it's like if the task I'm doing is detecting whether food has gone bad, right? Like going from the level of food manufacturing to like all of manufacturing doesn't change very much the level that you of the sort of number of tasks like that you could aggregate up. Yeah. Okay. So the problem with this AI as a service thing, right, is that it still does take a long time, right? If you ever have to have that, like, actually you have to do some customization, you have to like, somebody has to go to your store, help you set up the iPhone so that it's pointed at the right place, like calibrate the system, yada, 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 right? It takes a long time. And just, to give you an example of this, like US self-checkout systems, right? Very generic, right? You can apply this in almost every place, right? The CAGR, 11% per year. Okay, so that's substantial, but it's not enough. Like, it's enough to sort of move things slowly over time. It's not enough to dramatically change the picture we just talked about. Okay, so now that's not to say you couldn't. I mean, I imagine there will be at least some AI platforms that people create that just turn out to be incredibly generic, right? And that you'd expect to happen more quickly, but I think a lot of it is going to fall into this. Okay, how about costs? So there are lots of reasons I think that costs are falling in AI in big ways. So some of the stuff that we've done in our lab, we've measured the cost improvement of GPUs. You get about 22% per year. Okay, so that's a pretty big number. The paper we have coming out in terms of efficiency, I won't say the specific number here because I don't want to, but it's even higher than that. Okay, so that's the efficiency with which we can use data and therefore the algorithmic improvement. So we have a bunch of things over 20%, right? Now, in terms of the cost of like the engineering, that's a little bit more dicey, right? Because on one hand, you do get like improvements. People build PyTorch and things like that allow you to build these systems better. On the other hand, like actually the labor cost is pretty expensive. And so if you actually have to hire these people, it's not at all clear costs are going. Okay, so what happens? Well, if you start from 2022, which is, we picked this is because that's when the census data we have that we're using, right? And you say, okay, well, what if we get a 10% annual cost decrease? So that's across all of them, right? Compute, data, engineering, all of these things. It actually takes a long time for the systems to spread, right? And that's just what Eric, you were pointing out. This is that fact that even when you increase things, right, because there's this long tail, you need exponential improvements to get linear changes, and you can see that, right? 20%, so closer to what we saw for GPUs. Assume everybody gets that. Okay, now it's a little faster, but it still takes quite a while. You really need quite dramatic, like 50% per year improvements for this to happen very rapidly within a decade or something like that.
Seems like there's two very different sets of costs. There's like the compute, the Moore's Law technology stuff, and then there's physically implemented. Like I doubled the amount of solar on my roof recently, and solar panels have gotten much, much cheaper. But the labor to put them on the roof, I don't think has gotten at all cheaper, or the opposite direction. And now most of it is the labor cost. Even if the panels were free, it wouldn't change the cost of putting solar on my roof all that much. So have you broken this into those two categories? Like one that I think plausibly would improve very rapidly, and the other, not so much?
Yeah. So precisely. I mean, that the intuition you've conveyed is exactly why I think that like many of these small deployments will just never happen for exactly the reason you just said. So we have. So for this, we haven't broken it apart in this particular one, but we certainly could. I mean, we have for all of these things because we build it up from the underlying cost. We have it. We just haven't reported it here.
Disease.
Exactly. So for those who don't know, Balmer's cost disease is just this idea that if you had two things that were 50% of your cost and one of them gets smaller really rapidly, the other one is the limit, right? And so in computer science we call this Amdahl's law, right? This is just the same concept expressed in economics or computer science language. Okay, all right. So in my last few minutes here, I just wanted to say, okay, so let's now think about.
By the way, there are some questions online. We've been holding them to just so you know.
Yeah. Okay. All right. So I got about 4 or 5 more slides and then I'll stop. Okay. So I just want to show you. So if we think about this trend, what we see here, right? So we see there's initially a big jump, right? We have this new technology, a whole bunch of tasks are going to be economically attractive to automate. That means we should expect a bunch of activity, particularly amongst big firms, right? And I think some of the work that Christina McElhern and Eric and others have done is really saying that, right? We see the big firms moving pretty quickly to try them down. And then we see a slower process going on over time as the diffusion has to go through the economy, and that's hard. Well, you can ask, how fast is this happening and how does this compare with the baseline rate of job replacements in the economy? And that's what this is showing. So this line up here is a line from John Hultiwanger. This is the US job destruction in the economy annually. And this is showing you what the contributions of these different changes would be. And you can see that if you had a 10% system increase, it doesn't actually contribute all that much. 20%, a little bit more, but it's still 2% on a base of this. And it's unclear whether you should just add this to the top, right? Because it might be some of the same jobs that you would have automated one way and now you automate another. At 50%, you do get more, but of course, at some point it falls off because at that point, the system has just done a lot. But all of this is telling you shouldn't think of this as like, oh my goodness, tomorrow, the unemployment job destruction is going to double, right? It says we should have an initial period, and then we should have a transition. And the question for this transition will just be, are we creating enough new jobs to account for these destructions we see? Okay. So lastly, let's just discuss how this framework applies to large language models. So I think the broad framework, absolutely still applies, right? We still should be asking, what level of performance do you need? How much does it cost to build the system? And where will it actually be deployed? And the question is just like, are there a lot of differences? And a particular, question here is, if we think about ChatGPT moving to GPT-4, moving to the recently trademarked GPT-5 that's coming, right? These ever bigger foundation models are improving performance, right? And so if you say, well, like more and more, that might mean that we don't have to have a lot of fine-tuning costs, right? We can just take the system off the shelf and use it, okay? And so in theory, you could get rid of the need for training compute, training data, and much of the engineering. So we actually modeled this in our paper. We said, well, in computer vision, let's imagine we had this incredibly good system. Actually, how much would that change our answer? The answer is it does change it, but not a ton. So we're going to assume data is free, compute is free, minimal engineering. Okay? And our estimate goes from 23%, about half. Okay? So it changes things, but still not all the way. Why? Because you still have, as long as you still have like some sales process, some engineering process where someone has to go to the little corner store and say, I'm going to set this all up for you. I want to charge you $1,000 to come. And the store is like, no, that does not make any sense for me. Then that task never gets out. Okay, and I will, I'm going to, given the amount of time, since I'm a little bit late here, I will just say the number of jobs, what our paper shows is that the number of jobs that are cost effective for firms to automate is much smaller than is implied by AI exposure. And this arises because there's a long tail of systems that are expensive to build. This new measure is a good predictor of observed unemployment risk. And initially, we expect a jump in automation, but then further adoption will require either industry-level platforms to get scale or deployment costs to fall. And language models will also be limited by deployment costs, albeit perhaps less because they could have greater scale, right? And that's one of the things that I think we're doing some work right now to extend this model to large language models and be able to say how much more scale do we actually expect. And with that, I'll stop and take questions.
Yeah, let's see questions in the audience here, right over here.
Yeah, so I guess picking up on the general theme of, you've got these long tail of tasks, and that means that like you're never going to automate everything. Like it seems to me there are like two types of long tail tasks. As in like one of them is just, the like nines of accuracy that you need for, I don't know, like, designing like a plain door is like clearly different to like bad strawberries or something. And like, here's like and that's like a task that maybe just never gets automated. But like the second kind is like the Walmart case, right? So as you said, like it's pretty easy for Walmart to be like, sure, train on all of our aisles and have a robot come in, and it's like hard for the corner shop to do this. But like it seems to me that like in one of these cases, like there is still a demand for airplane doors, but it's not entirely obvious to me why the corner shop just doesn't disappear after 5 years when like Walmart has like perpetually lower costs. And so my question is like, does your analysis like mostly focus on the case where like, yeah, or like it does it look at mostly like the partial equilibrium thing of just like what happens to these costs, or does it look at the general equilibrium thing of like, but some of the places where they can't reduce the costs just disappear, and so those jobs but they disappear for a different reason, not because of like lack of automation or whatever.
Yeah. So great question. So first of all, I like your shirt, by the way. That's the scaling, one of the scaling law equations for those who don't know. Yeah. So I think there's sort of two answers to your question. So one is like, why should you expect the small store to continue to exist when Walmart gets more efficient? The answer is just that like a lot of these things that we'd be automating are not that big a share of costs, right? And so if you say like, growing up, there was a bakery that we used to go over to over the summers, right? And basically nothing about it was efficient, right? You had to stay there for a long time, whatever. But you walked in, it smelled of wonderful food. It was sort of a lovely way to spend a morning to go in and get it, right? And so, like, it doesn't really matter that, like, the Walmart might be better. Like, if there are lots of other things that determine customer preferences, and that's why, like, in the economy, we see huge persistences in like some areas of the economy are very efficient and some are very inefficient, and we see those existing for a long time. But I think the other answer to your question is that even having said that, we should absolutely expect like a change to happen, right? Some new store gets created. The new store would say, well, why would I use the human if I can do an off the shelf system, right? So you are going to get that. You're going to see shares in the market change hands, right? And so that would fall when I talked about the AI platforms, right? All of that is saying like, oh, okay, well, if you got 10% more per year or something like that, you do get this escalation, right? But again, it just takes a long time for it to spread. Yeah.
Take a question from online. So what happened to it? Yeah. Bring it back here. Sorry. Well, if I can remember what. Right.
Oh, we have another one in the room.
Yeah, okay, let's do the one in the room.
Yeah.
Do you have a sense like how these computer vision, this job replacement, how that differs in its effect on productivity relative to like the narrative around like industrial robots, like who have maybe taken a lot of jobs? Do you have a sense that these are like nuisance tasks, like the baker actually wants to bake bread and not like check whether something's expired? So like sort of related to this value multiplier you talked about.
Yeah, so I'm not sure. I feel like I have enough of a sense of, I mean, the vision tasks across the economy are incredibly diverse, as you can imagine, right? So, I mean, I gave you the example of a retail worker. Another one is like anesthetists. When you go under anesthesia, they're like monitoring your eyes and your color to make sure that you're not in distress. Like bricklayers are looking to make sure that the walls are straight. Like there's just a whole, so I'm not sure I feel like I can generalize. I mean, certainly a bunch of them you could imagine saying, oh, I could imagine having this and taking it out of someone's job and then being more productive in other things. And other ones I could imagine it being like, oh, like how much time are you really saving the baker, right? Like they probably, as they're picking up the food is probably when they're checking whether it's bad, right? And so I'm not sure that's really a nuisance task as much as it is like them assessing it and stuff like that. So I think you're going to see both. And I'm not sure I would say broadly that it would fall one way or the other.
The question here from Arnie Milstein online. For what percentage of work done by humans do we have decent information on inaccuracy rates? Knowing this seems like it'd be important to estimating the value add by AI. So you showed those scale laws for the computers, but what about the benchmark for humans who we're comparing it to?
Yeah. So this is so as far as I know, there are sort of no broad data sets that exist on this. We actually did some very large scale survey work on this to do it. And so we have like quite a detailed database about computer vision accuracies that you need. And in fact, we will be releasing that in a little bit. We're also doing that for large language models and stuff like that. So we are building these, but yes, I mean, the level of proficiency you need is incredibly important. And what we realized as we were piloting the survey is you actually have to ask the question a number of ways as well. And so, for example, like one of the things you can ask is like, what's the level where if the human performed worse than this, you'd fire them, right? And that starts to get at that sort of threshold of, okay, the system really has to be at least that good, or you don't want to have it replacing the human. As an example, yeah. Cool. We have another one over here.
Well, you've started with the assumption that there's certain areas where you're going to use computer vision related things. It strikes me that as we're looking forward, as opposed to backward, there are going to be so many fields where either computer vision becomes relevant because of retooling in those industries, or where computer vision becomes totally irrelevant, but the gains or losses of employment from other methods that are not computer vision are going to far outweigh that.
So let me just paraphrase, make sure I understand. So your intuition is just that the job creation that's going to come from this, or the task creation that's going to come from this, either being in existing fields but adding computer vision or totally new applications, that effect is going to be very, very large and outweigh these losses that we see.
My assumption is that as all of these industries retool, redesign their processes, in fact, computer vision is just going to be one small part of it, and that the effect of the other kinds of retooling are going to far outweigh in terms of employment and other.
Oh, in terms of other types of AI that we might deploy, absolutely. And I should have been more clear about this. So the reason I came back at the end and said, well, how much should we think of this applying to large language models and stuff like that, is precisely that intuition, right? We should not expect computer vision to be like the thing that puts people out of work, but we should expect the economics of computer vision to be quite similar to the economics of large language models, with a few exceptions, right? And that's just because you're still going to get these scaling laws, you're still going to get like the small players, you're still going to be high accuracy is really expensive, right? And so the real change is going to happen if you get more scale, right? Or if you can use these large language models more often without having to fine tune, right? And so that's precisely where we are going to go. And wait 4 or 5 months, and we'll actually have a more detailed answer for you on that one as well.
All right, thanks, Neil. I'm sorry we're out of time, but really appreciate the talk. Glad you came all the way out here to rainy California. So next week we have, actually on March 4th, we have Gillian Hatfield from the University of Toronto. So see you all then. Thanks.